Welcome to your first lesson on Module 5, Equilibrium and Acids. So the first topic that we're going to be looking at is static and dynamic equilibrium, and I've broken this down into 4 subtopics. So let's begin. Irreversible reactions. So what are irreversible reactions? Irreversible reactions proceed in one direction, and that is the forward direction only. And so that's why in our chemical equations for irreversible reactions, so for example over here, we have the chemical equation for burning steel wood, which is an irreversible reaction. The arrow is only pointing in one direction, and that is the forward direction. So this is another example of an irreversible reaction, which is the burning of magnesium. And we can tell that it's an irreversible reaction because, again, the arrow is only pointing in one direction, and that is the forward direction. So in irreversible reactions, what it means is that once all of the reactants have been converted into products, the products are not going to be turning back into reactants. So over here, once all the magnesium and oxygen have reacted with each other to produce magnesium oxide isn't going to be turning back into oxygen or magnesium. Instead, the reaction just stops. The reaction finishes. And when the irreversible reaction finishes, we say it has reached static equilibrium. So at static equilibrium, the concentration of our products and our reactants, they are constant, and the rate of the forward and reverse reaction are 0. So we'll come to explain that statement a little bit more later on. So we're moving on to our reversible reactions. So in Module 5, the reactions that we're mainly going to be looking at are going to be reversible reactions. So reversible reactions, they proceed in 2 directions. That is the forward and the reverse. And so that's why in chemical equations for reversible reactions, we use an arrow that points in 2 directions. So for example, we have this reversible reaction, and we know it's a reversible reaction because of the arrow that is used. It's pointing in 2 directions. So what does it mean that reversible reactions proceed in the forward and reverse direction? So let's take a look at this example. What it means is that nitrogen and hydrogen are reacting with each other to produce ammonia. So this reaction over here, this is our forward reaction, indicated by the arrow pointing in the forward direction. What it also means is that ammonia is also decomposing back into nitrogen and hydrogen. And so this is your reverse reaction, indicated by the arrow that's pointing in the reverse direction. So reversible reactions, they have 2 reactions or 2 components, the forward and the reverse. So reversible reactions, they don't actually go to completion. Instead, they reach something called a dynamic equilibrium. So what is a dynamic equilibrium? A dynamic equilibrium is when the concentration of the reactants and the products become constant at non-zero, and the rate of the forward and the reverse reaction are equal, again at non-zero. So what that means is that once a reaction has reached dynamic equilibrium, if we were to look at our reaction or vessel, for example, for this reaction over here between nitrogen, hydrogen, and ammonia, at dynamic equilibrium, we're going to have some nitrogen present, we're going to have some hydrogen present, and we're going to have some ammonia present as well. Okay, so this is, for example, how a system at dynamic equilibrium would look like. We have nitrogen present, we have hydrogen present, we have ammonia present. So all of the species are present. And number 2, the concentration of all of these will remain constant. So what that means is if this system has reached dynamic equilibrium at T is equal to 10, then at T is equal to 20, the reaction vessel will look exactly the same. It's going to remain the same. The concentration of nitrogen, hydrogen, ammonia, it isn't going to be any different at T is equal to 20. And the second feature that we mentioned was that the rate of the forward and reverse reaction are equal. So what that means is that the time or the rate at which nitrogen and hydrogen are reacting with each other to produce ammonia, that is going to be equal to the rate of the decomposition of ammonia as well. So there's basically going to reach a time when nitrogen and hydrogen are going to react to produce ammonia, but at the same time, that ammonia is going to be immediately decomposed back into nitrogen and hydrogen. And so overall, there's not going to be any change to the amount of nitrogen, hydrogen, or ammonia present, because as soon as it's being produced, it's being decomposed back into nitrogen and hydrogen. And that is why the concentration of our reactants and our products remain constant, because the rate of the forward and the reverse reaction are equal. Okay, so let's have a look at this HSC question over here. So